Hi everyone, so welcome back to our YouTube channel, Becoming a ROS Developer. Today we've got Benedictus, who has just completed the course ROS 2 Basics with Python, and he'll be giving us a demonstration on the real robot before getting into the details about his project, how he has managed to get the task accomplished. So what I will do now is hand over the floor to him so that he can begin with the demonstration, and then we'll get into the nitty-gritties of his project. All right.
All
Whenever
right.
you're ready, Benedictus.
Yeah. Greetings. My name is Benedictus, and I will present to you my results for the ROS 5 days course.
Uh-huh.
I will start the robot now.
All right.
First, it will find the wall. Now, it already find the minimum distance, and it will get closer
Mm-hmm.
and adjust itself before the wall following starts. All right. It has started the wall following process, and as you can see, there's the feedback from the actions. So it tells us how far the distance is.
Mm-hmm.
And I also added the logger to make sure how much distance traveled from the origin. So if it's closer, then it will be getting smaller.
Mm-hmm.
So as you can see, distance from starting post, basically the magnitude from the original position.
Mm-hmm.
Right. As you can see, the wall following process is done correctly. Uh, I encountered some issues when it already is in the starting position, it doesn't stop. So I enlarged the I enlarged the minimum distance from 0.05
Mm-hmm.
to zero point 0.1. As you can see, it already stopped
Okay, I see.
and it has recorded 60 points, which means it recorded each second, so 60 seconds, about 60 seconds.
Okay.
So yeah, it has ended,
All right. All right.
right? So I think I will get into the details now, if
Sure.
you don't mind.
Sure. Let's go.
All right, let me start presenting. Again, my name is Benedictus. I'm a PhD student majoring in electrical engineering and in the University of Houston and recently admitted this spring semester.
Mm-hmm.
My research interest is robotics and control theories.
Mm-hmm.
And I just want to recall the objective. Is the first one is to find a wall, second is to follow the wall, and third is to record the odometry.
Right.
And there's a little bit difference between the robot and the gazebo simulation and the real one. So the laser index is different. In the gazebo, the front is zero index the first index, and the right laser is 540.
Mm-hmm.
While in the real robot, the front index is 360, while the right index is 180.
Right.
Yeah, so I had to adjust from the simulation and the real robot. I did trial and error, and yeah, as you can see, it works perfectly now.
Okay.
So the topics used, first of all, is the command velocity. Basically, we want to publish the velocity to the robot, like the linear and the angular velocity.
Mm-hmm.
And the second one is scan. Scan is to get laser data. And finally, the boundary or the Adam, we want to because we want to track the robot's position.
Okay.
So yeah, and this is the launch file that I make. So we can run multiple nodes at the same.
Mm.
First one is the wall follower,
Mm-hmm.
which is the main node. The second is the wall finder. It is a service server, and the third one is the odometry executable is the action server.
Okay.
So this is the connection between the nodes. As you can see, uh, the wall following robot node is the main node, and it subscribe to the laser sound, so it can get the laser, so it can measure the distance between the right and the front of the wall. And it is also connected with the bottom recorder, the status, the final status, and the feedback. The feedback is the current total distance.
Right.
And finally, there's the final wall server, also subscribed to the scan. Basically, it's used to find the wall, the nearest wall. And the wall following robot is publishing the command velocity in the and the one wall server also publishes command velocity best with the move to the wall.
Right. Okay.
This is the simplification of the wall finder process. So first of all, we will scan the surroundings. We use all the index, the readings, and we want to find the minimum of the index. And after we find the minimum, we move to the index. So basically, I rotate the robot so that the minimum index is can be found in the front of the laser. So,
okay.
For example, if the minimum is in the back of the robot, then it will keep rotating until the front reading is the minimum reading.
All right. All right.
And after the minimum reading has been found in front, then it will move closer to the wall. So for this case, only the linear velocity command. And if the front is bigger, the reading is bigger than 0.3, then I will move the robot. And if it isn't, then I will not move furthermore.
Okay.
And after that, we want to adjust the robot so that the wall is on the right hand of the robot. So I rotate counterclockwise so that the right is the minimum because that's the closest distance.
Okay.
And next one is the wall following. So basically, for the wall following, I only use the front and right because yeah, that's the minimum requirement. And the logic is if the front is bigger than 0.5, then it will keep moving.
Right.
But if the front is less than 0.5, then it will turn left, but it's still moving linearly, so that it doesn't stop. So, the next one is if the right reading is between 0.2 and 0.3, then the robot will just keep moving forward. There's no need to adjust the orientation to be closer or to further from the wall.
Okay.
If the robot's right is readings larger than 0.3, it will move forward while turning a little bit right. So it can adjust between 0.2 and 0.3. However, if the reading is below 0.2, which means it's close, very close to the wall, then it will move a little bit fast.
Okay.
And finally, the odometry. Again, this is a simplification. So first, we take the odometry data and we calculate the distance, and then we send the feedback. And if the position of the robot is near the starting position, then it will stop. So yeah,
All right.
this is the simplification. The conclusion from the experiment, as you can see, the robot can successfully find the nearest wall, and the robot can follow the wall, and the odometry can be recorded and can stop after it finally reaches the starting position again.
All right.
While the possible improvements that I can think of is for the wall filling process, I only use the EFL statement, which may look kind of rough on the surface. So maybe we can use a controller, maybe a PID or something to make the wall following process smoother.
Yes.
And the last one is to utilize the calculated distance, because from what I read from the requirements, we only calculated the magnitude from the starting position to the current position, but the total distance is not utilized. So, yeah, I think we can utilize that.
All right. All right.
I think that's it for me. Thank you very much for listening.
All right. very nice presentation, Benedictus. So thank you for getting us through it nice and smooth, and also highlighting some of the things that you did to fix the issue with not finding the right position to stop right at the very beginning. Because
Yep.
would want to know what led you to figure out that maybe if you put the minimum distance to like 1, that's 0.1, right? If
0.1,
zero
yes.
point 0.1, yeah, to 0.1 it will enable you to the robot to stop. Did you do trial and error? How did you figure that out?
Yeah, actually, in the simulation, it can stop at 0.05
Okay.
every time, but
Okay.
in the real robot, it's obviously different.
Yeah.
So, because the success rate with using 0.1 is bigger than 0.05, then
Right.
yeah, that's why I modified it.
Right. Very nice. So, the other thing I wanted to find out is so for your basically, let's say your control loop, right? You did an if statement, right? You kept on checking the range of the range between the robot and the right wall. Is that right?
Yes, so here it is, the front. This is to check if the front is lower than 0.5. This is the part to adjust the
Okay.
wall.
Okay, I see. I see. All right. So you put it into segments to say if it's below this, then I'll make it tend to this, to the left or to the right, depending on whether the number is below that threshold.
Yeah, that's right.
All right.
So
Okay.
basically, uh, I'm using the fan. So if the fan is triggered, the new command clause will be published, something like that.
All right. All right. You also mentioned about on your flow diagram there was some other node that publishes command velocities, right? Oh yeah, the find wall saver, right?
Yes.
Can you take us through the logic of why that happens, right? Why does it end up having to publish command velocities?
All right. So in the for finding the wall, I'm using a
Mm-hmm.
service server.
Mm-hmm.
So and the service is synchronous, which means that it will block all other processes
Right.
before. So all other processes will be done after the service is done. So
Right.
yeah,
I see.
that's why I added another what do you call it? The command velocity.
Mm-hmm.
So yeah,
So okay,
that's my reason.
so let's say your server publishes the command velocities after it's done, right? Um, to which callback or to which service or action or whatever, to which of those does it hand over control to, right? Because it's just saying begin moving, for example. That's what publishing command velocities does, right? But who is taking over control after that? That's what I want to understand.
Oh, let me reiterate that. So in the following for the main script,
Mm-hmm.
I call the server, right? The service server,
Mm-hmm.
and it's synchronous. So all processes in this script will be blocked and it will process in the action in the wall finder server.
Mm-hmm.
So first of all, it will receive the request, and it will first rotate to the nearest wall.
Mm-hmm.
Is this one? So yeah, I in each method there is command flow to be published. So yeah, so after I find the wall, the next step is to adjust the position, adjusting the position. So yeah, there's also the command to publish the velocity as well.
Mm-hmm.
And then there is after this is done, then we adjust the rotation so that the wall is on the right hand of the wall.
Oh, okay.
There's
All
also
right.
the published velocity as well.
All right. All right. I see. I see. All right. Let's see if I have any questions for you. Not anymore. All right. So a very nice presentation. congratulations on figuring out how to make it stop eventually, because that is a thing on its own, right? You have to understand what to tweak and what not to tweak, right? So very nice presentation, Benedictus. I would like to say for now we can conclude here, and then we'll finish our conversation on Zoom, all right? So just hang on.
All right.
All right, so this was Benedictus' presentation. So congratulations to him on a very nice, well outlined, detailed explanation about how we went about getting the task completed. So until next time, we highly recommend that you take a look at some of the courses we offer, certification online, and then you can give them a shot. And then until next time, keep pushing your